Hello and welcome to Science Talk. I am your host, Jim Massa. I want to discuss with you in this video a story that is quite interesting and may rewrite our understanding of when life began on this earth and evolutionary processes. This involves fossilized microbes. Of course, microbes are too small to be seen with the naked eye, and basically the microbes in question were first unearthed in Western Australia in 1982, and they were described in 1993. At the time, there was a debate among scientists as to whether these represented actual biological specimens or were perhaps simply minerals. A new analysis has been performed on these specimens, and originally the specimens were thought to be about 3.5 billion years old. Well, in a re-examination of it, and I'll get to this in more detail in a bit, the diversity of the microbes suggested that life on Earth probably emerged even earlier. There are some experts who actually think that there are other samples yet to be found that could even be older than the Australian microfossils. So, the first life on Earth, as you probably might recall from your general science classes, was microbial. And fossils from this time, 3.5 billion years or so, offer a tantalizing glimpse of the forms from which all creatures, living and extinct, evolved over billions of years. Now, just when you think about it alone, Earth is about 4.6 billion years of age, and within a billion years we have life. Yes, microbial, probably bacterial in nature, or something akin to bacteria, but still, that's pretty incredible. In recent years, other studies have reported microfossils holding evidence of ancient microbial life, such as tiny hematite tubes embedded in iron-rich volcanic rock in Quebec. Hematite, of course, is a reference to iron, which may have housed microbes that lived between, in essence, 3.8 billion and 4.3 billion years ago. Another study described cone-like structures detected in rocks in southwestern Greenland, which could represent sediments surrounding fossilized microbial colonies living 3.7 billion years ago. You kind of get the picture. We're now finding evidence even further back in time for ancient life. So, going back to the specimens in question here, this new investigation examined these fossilized microbes. They looked at not just, with the shape of it, they looked at the geochemical signatures in the samples. John W. Valley is a professor of geoscience at the University of Wisconsin-Madison, and he is basically the lead principal investigator into this study, and he was the one that basically said that that's what they looked at, is the geochemical signature. Okay. Now, of course, this is very, very tricky. The stuff has been sitting there for billions of years. There's a lot of chemical processes going on, chemical weathering and so on in the rocks there. So this can affect the specimens, and you have to be very, very careful with your analysis. And for this very reason I just said for you, analyzing these specimens were difficult. Okay. William Schaff is a professor of paleobiology at the University of California in Los Angeles. He was a co-principal PI researcher on this study. He was also one that found the specimens years ago. And what he did was they examined 11 of these specimens, and they used a new technique. And the new technique is extremely highly sensitive, and was of course not available when the microbes were first described. And this technique is called secondary ion mass spectrometry, or SIMS, S-I-M-S. This procedure analyzes the composition of a solid surface by blasting it with ions, and then collecting and evaluating the ions that are ejected from the scanned object. So how do we do this? Well, you have to very carefully and meticulously, you have to expose the fossil's surface, so you have to carefully grind it down, the rock that held the fossil. It's almost like, you know, digging out the rocks from fossilized bones. Here we're doing it on a micro level, even more delicate work. So after they did this, and after they then scanned the fossil, they isolated and compared the carbon isotopes. Okay. Now, let's take a moment to discuss what's meant by isotopes. Each element has its own atomic number. An atomic number is the number of protons that are found in the nucleus of the atom of the element. You change the number of protons, you get a different element. So carbon is atomic number 6, meaning it has 6 protons in its nucleus. If it does not have 6 protons, it is not carbon. However, there's also a thing called atomic mass. And atomic mass, generally speaking, is the sum of the number of protons found in the nucleus plus the number of neutrons found in the nucleus. Electrons, though they have mass, it is not significant in any real sense of contributing to the overall atomic mass, as protons and neutrons are much more massive compared to the electron. So isotopes are basically different forms of an element, with meaning that there are different numbers of neutrons. So the most common form of carbon is carbon-12, C12. That means there are 6 protons and 6 neutrons. Carbon-13 has 6 protons, 7 neutrons. Carbon-14 has 6 protons, 8 neutrons. So by changing the number of neutrons, you get different isotopes of the element under consideration. O16, oxygen 16. Oxygen is atomic number 8. That means there are 8 protons in the nucleus. Well, if we have O16, 16 minus 8 is 8, so it would be 8 neutrons. Well, there's also oxygen 18, O18, where we have, again, the 8 protons still, but now we have 10 neutrons. Nitrogen 14. Nitrogen is atomic number 7, 7 protons. Nitrogen 14 has 7 neutrons. Nitrogen 15 has 8 neutrons to go along with the 7 protons. I think you get the idea on that. Now, I will be discussing in other videos of the importance of looking at the ratios of, say, C14 to C12, C13 to C12, O18 to O16, especially in looking at paleoclimates. These ratios are used to ascertain what sea levels were, by looking at the ratio of these elements, of these isotopes, within, say, the test of radiolarians, foraminifera, and so forth. That's another video coming later. So, what they looked at here, they looked at the ratio of C14 to C12 as well as C13 to C12, but mainly the first one, C14 to C12. It's in a process called fractionation when you examine these ratios. And what they found was that the ratios of 2 particular isotopes are characteristic of biology and metabolic function, Professor Valley said. Okay. We show that taxa identified by morphology correlate to carbon isotope ratio. You're going to love this one. It took them 10 years to develop the ability to make these measurements accurately. If you're not a patient person, you probably should not go into certain fields of science. But in looking at, again, looking at the features here, looking at the morphology, looking at the chemistry, looking at these ratios and so on, they were able to identify these microbes as a diverse group. Some of these microbes were methane producers, which makes sense because 4 point something billion years ago, there was no oxygen in the atmosphere. That came later. So most of the early life were probably methanogens, meaning that they utilize CH4, methane, for their metabolism, their biological processes. Here's the thing, the differentiation between these microbes suggests that life had already been on Earth long enough for there to start the process of diversification and specialization. So while it's impossible to say when life made its first appearance on the planet, these microbes hint that life has been around since 4.3 billion years ago. So that definitely pushes it back. If Earth was formed 4.5 to 4.6 billion years ago, in a mere 200-300 million years, boom, there's life on this planet. That's rather remarkable when you think about it. And then you can start thinking, well, especially now with all these exoplanets that are being found and discovered, what does that hint at the possibility of similar processes occurring elsewhere? To me, it is mind-boggling, the ramifications of this, not just for Earth, not just for how evolution proceeded here on this planet, but elsewhere in the galaxy, elsewhere in the universe. Come to the end of this short video. If you are already a patron and a subscriber to my channel, I thank you for your support. If you're not, I hope you will consider supporting my work by going to patreon.com/Science Talk with Jim Massa. Tell others, spread the word. Thank you for your support.